UC Irvine, who's going to be talking about the intersection of physics and machine learning.
Yeah, thank you very much for the kind introduction, and thanks everyone for still staying here this late afternoon. Yeah, so I'm going to put my theoretical physicist hat on. I've been actually doing theoretical physics more than 10 years ago, but not for the last 10 years. And so now I'm in the computer science department. But for this talk, we'll talk a little bit about a physicist's perspective on diffusion models. And this will have two parts. First, I will basically try to tell you how like a thermodynamics perspective on diffusion models can be very helpful for designing new models and making them faster. So we'll talk about understanding the design space of diffusion models. We talk about efficient samplers, and also how you can actually compress and communicate data with diffusion models. Then the second part, if time permits, I'll talk about applying diffusion models in the space of thermodynamics. In particular, we'll look at atmospheric convection and climate science. So yeah, diffusion models have been applied in a variety of contexts. Here is a picture of myself being desperate about worrying to compete with industry research. And we're all, of course, used to seeing these pictures over and over again. There's a little bit of work to be done in terms of the grammar, but otherwise these methods are working surprisingly well. Also, diffusion models have been very successful in terms of video generation. There's been some almost historical work on the left-hand side by our own group from 2 years ago, doing sort of first steps in this direction. And nowadays, we're even used to seeing these sort of amazing results. This is like a Sora video generated based on a prompt that shows, show me a video of the California gold rush. And this could be literally taken from a Western. So it was actually a time where I was really concerned about these developments and how we as academic researchers can still do meaningful contributions to this world. But hopefully after this talk, you'll have a couple of fresh ideas of how we can still be relevant here. Yeah, diffusion models have been used and are actively being used in climate science. So there are some results on super resolution for precipitation, in other words, rain fields on the globe. I'll talk more about that later. And there's also interesting developments on using diffusion models for compression. So what you see here is a sort of a neural, so in other words, deep learning-based compression approach. You see there's an image of a parrot, and then the diffusion model actually faithfully reconstructs this more or less, faithfully reconstructs the parrots. If you look closely, there are slight variations in terms of the texture, but those are certain details that we can abstract away. If we're willing to tolerate these sort of unfaithful reconstructions, we can actually get pretty amazing lossy compression performances with diffusion models. Again, as I talked or said already earlier, today we'll talk about sort of a physics perspective involving information theory, kind of thermodynamics, and generative modeling. And I'm by far not the first one who is kind of bringing this up. Actually, if you look at the old papers on diffusion models, you'll see that this actually all started with theoretical physics, right? I mean, Sirian Ganguly and Yasha Sol-Dickstein, this group from Stanford, they're all physicists, and they came up with diffusion models in 2015, inspired by their earlier work on non-equilibrium thermodynamics. So hopefully we'll get some time to get into this. Like those are sort of descriptions of non-equilibrium processes that are not reversible, that have like some entropy production. And it also connects to information theory and efficient data communication. OK, to get started, I would like to kind of get everyone sort of on the same ground and talk a little bit about diffusion model and primarily where diffusion model actually originally comes from. Turns out Brownian motion can be roughly described as follows. You have a single particle that you observe, maybe under a microscope. And this particle is surrounded by a group of smaller particles. And with these particles, it undergoes frequent collisions. Now, the important part is that the system as a whole is actually deterministic. It solves sort of the Hamiltonian equations of motion. But if you only focus on the single subsystem, the red particle, it appears as if it were stochastic. And then based on this observation, mathematicians developed essentially a mathematical formalism, which is that of continuous time stochastic processes. Oftentimes, they're described in terms of these stochastic differential equations. We have changes in the position. The x is given by some drift, f, that depends on x and time. And then there is some additional diffusion or some stochastic noise insertion, dw, which is called the diffusion term. Now, in the image domain, we're basically simulating exactly this process. You see an image of a dog, and I'm sure you've many times already seen these results before. We successively add noise to this image until we destroy all information contained in this image by following this forward stochastic differential equation. It's pretty much the same one as shown before. But then magically, when you reverse the error of time, you can actually then learn the reverse process, right? And this is essentially what we are interested in when we do generative modeling. Turns out that if you flip the error of time of the stochastic differential equation, a new term emerges, and this has something to do with the gradient of the log data density, in other words, the score. And this is quite natural, namely, in order to kind of find back your way to the data distribution, you have to basically climb uphill, right? So you need a notion of data density, and the gradient of the data density enters here. But this is also called the score. Let's revisit these processes again in a little bit more detail. And here I want to introduce a slightly more general notation. Now I call Z the collection of pixel space, X, and potentially some additional dimensions, M. We can think of them as momenta, right? But in general, M can be any extra dimensions that we would like to model with and work with. Now, the forward process here in slightly more simplified version reads as very similar as before. dz equals f times z, so in linear term, plus g, a diffusion matrix, times dw. Right? And this process is, again, the process that destroys information. It runs forward in time, and so it can only increase entropy. Yeah, usually this has no trainable parameters, and we ultimately only want one thing, namely that this process actually converges to a distribution that we can easily sample from, so that when we ultimately invert the process, we can start from that distribution that the forward process converges to. Now, flipping the error of time again, we get this reverse process. Again, we have the score entering the gradient of the log density, P of z. Unfortunately, we don't know this, right? This is actually the whole complication. We don't know the data density. But if we knew it, then this would be exactly the reverse of the former process. And it turns out that although we cannot immediately train the score, although we don't know the gradient of the log density, there are certain tricks that nevertheless allow us to train the score and approximate it using a neural network. Right, so now the gradient is given by s theta. It's a trainable neural network. It depends on position zt, and it also depends on the time index t. And so this process reduces entropy, right? It goes from high entropy down to lower entropy. And we'll skip the details of how these scores are being trained. It's basically a regression task. OK. So let's talk about the first part. How do we use our physics knowledge in order to come up and improve existing diffusion models? Now, first of all, it turns out that the design space of proposed diffusion models is pretty large. There have been very basic diffusion processes that were proposed, and there are more advanced versions of it. On the left-hand side, we have one of the most basic constructions. So this is just the variance-preserving stochastic differential equations, or Ornstein-Uhlenbeck process, as it's also known. In this case, f is just a kind of scalar, right? F is just proportional to the identity matrix. Beta is a schedule that may change over time. And then also the prefactor of the diffusion coefficient dw, in other words, capital GT, is also just a scalar. Right? So this is a fairly simple basic process that we can easily invert. On the right-hand side, we have a more sophisticated proposal. This is a paper by NVIDIA, and they actually came up with a phase space formulation. Right? So you have not only position, but you also have momentum. Basically, f here is the deterministic part of Hamiltonian's equation, right? I mean, changes in momentum are converted into position, and changes in position are given by momenta, and changes by momenta are related to forces and stochastic noise. And this has been also very successful. Turns out with the addition of momenta, essentially the trajectories become smoother, and basically the hope is then if the trajectories are smooth, you can actually simulate these diffusion equations with a rougher time discretization. So ultimately accelerate sampling. Now, the question is, do I have to be a physicist to come up with these ideas, right? I mean, is there maybe a mechanism that allows us to invent all sorts of possible diffusion processes without necessarily being inspired by theoretical physics, right? So how can we explore the design space? And in particular, we still want to work with these augmented dimensions, right? These extra dimensions that make our trajectory smoother, but they don't necessarily have to be momenta. So for example, the dimension of x does not necessarily have to be the dimension of m, as demanded by physics. Also, the noise sources that we add don't necessarily have to correspond to thermal noise, right? And also, the drift forces don't necessarily have to be conservative. In other words, they don't have to be gradients of scalar potentials. Now, this opens up a much broader space of models. And so let's try to explore this design space in a little bit more detail. In particular, I would like to present a complete recipe for designing these diffusion models. To do that, we need a couple of assumptions. First of all, I assume that z, my joint coordinate, consists of my original position coordinate, x, and also some extra dimensions, m. I also demand that I ultimately restrict my attention to continuous time stochastic processes of the following form. So Markov processes that have some drift term f and that have a diffusion coefficient matrix D that is diagonal. And also, we demand that we converge to a pre-specified prior, right? So in other words, the distribution that the process converges to is something we would like to dictate so that we can easily invert the process. And a simple choice here is to write this down as a Boltzmann distribution, e to the minus h, where h can be some sort of, for example, some quadratic. In this case, some quadratic. In this case, we would actually converge to a factorized Gaussian distribution in position and in momentum, right? So that is something we can really easily sample from and invert the process. The result is then that there exists a complete parameterization of all possible such diffusion processes, which is given by the following formula. The drift f has to be a combination of diffusion D, which we pre-specified, and plus some skew-symmetric matrix Q, multiplied by the gradient of our Hamiltonian, which is the distribution that we converge to, plus some tau, which is a source term. And the source term is basically given by derivatives of D and Q. Now, it turns out that this is not a completely novel result. It turns out that this is actually borrowed from earlier work in the stochastic gradient MCMC literature, right? So there's already some work on characterizing all possible Bayesian MCMC algorithms that ultimately converge to your Bayesian posterior of interest. It turns out that this can be also applied to diffusion models. In this huge design space of possible diffusion models, we came up with one particular proposal. So here we again work in a joint coordinate between position x and momentum m. Both of them are coupled by this matrix involving the coefficients m, the mass matrix, then there is a damping factor gamma, and then there's like another constant mu. And interestingly, there are now two different noise terms. There is a noise term in position space and an additional noise term in momentum space. I could not think of any physical system that has this property. Maybe this exists, but usually noise, thermal noise, only couples to momentum. So this again illustrates that this general recipe is actually more general than possibly inspirations that you might get from physics, right? So it turns out that this noise in both coordinates actually improves, has favorable convergence guarantees. This also gives you more tuning parameters. And in particular, when you then compare this to a variety of other samplers, it turns out that this also has very nice sort of trade-offs between the how quickly your sample quality improves on the y-axis as a function of neural network evaluations. Back in the days, in fall 2023, those were actually sort of pretty much state-of-the-art image results. Of course, the field has changed and improved so fast that nowadays this is no longer state-of-the-art. Yeah.
One very basic question. How do you compute the momentum of an image? What is
the momentum term?
Yeah.
Oh, it's just like some extra dimensions, right? So basically, you solve a so those are called auxiliary dimensions. They basically expand your sample space, but in the end, you only pay attention to momentum, to position, right? It's a little bit like Hamiltonian Monte Carlo, if you're familiar with MCMC sampling, where you also ultimately want to sample from some parameter space, and then you double the degrees of freedom and sample in an expanded space, because that algorithm converges faster.
I had another question. Yeah. Did you emphasize there was this P distribution, which you said was Gaussian? One more.
Here?
Yeah. So this simple pre-specified prior. I thought that the whole point was that this P distribution is very complicated and you can't write it down. So why are we putting assumptions?
So P, the distribution that you converge to ultimately is actually the pure noise distribution.
I see.
Yeah, it's not the data distribution. Yeah.
Thank you.
Okay. Maybe one quick question, since we're why does it need to be a Markov process? And in the spirit of sort of going beyond the physics that one would intuit, could you have a memory term?
You could have a memory term, and then this framework wouldn't apply anymore. That's all, right? It's just like for this kind of restricted class of processes, we can basically give a complete characterization. Good question. Okay. So this is interesting. But it turns out, unfortunately, in many situations, we don't actually have the capacity anymore to train the models ourselves, right? I mean, in many cases, we want to do an experiment, but we would need thousands of GPUs to do so, and we don't have it. So it would be really nice if we could do some research that is maybe a little bit more on the mathematical side, that just downloads an existing diffusion model and actually improves sampling in this trained model without us having to retrain the model at all, right? Is that actually possible? Right? Can we just look at the equations, improve them, and get suddenly much better results? And to this end, let's actually look at the reverse process for a fairly general class of models that are wrote down. Remember, there's the drift term, which actually could be solved analytically if there was no score, right? So this is a fairly simple term that, in principle, we could integrate out. And also, there's like a diffusion matrix, and this can actually have make the geometry in which we sample worse. Right? So you can think of that this combination of drift and diffusion terms have actually ultimately lead to an ill-conditioned geometry that we ultimately would like to improve, essentially by techniques such as preconditioning. Yeah? So the idea then is to change the coordinates before we simulate these equations, such that the geometry is better behaved, and we can actually simulate these equations on a sort of smoother trajectory. In other words, we can afford like a rougher time discretization. Yeah, there's a question here.
A noise term on the positions. Normally, a big gain that you get in a molecular system corresponds to having, the additional stability conferred by having only the noise term and the velocities. And then when you go to discretize the integrator, you can make it fourth order, for example. So when you add the noise term, don't you lose all of the benefit that you get from a finer discretization when you trotterize?
So yeah, we did different things, right? So in this work that I just talked about, we only explored sort of the Euler discretization. There we only saw the benefit. We also had subsequent work that actually looked at kind of more improved samplers. Let's talk offline about it. I think this is like going a little bit far.
Yeah, maybe like a follow-up of Grant's question. So when you augment the position with the velocity, does that actually make it harder to learn a score because the score is now a function of 2D dimension instead of D compared to the standard OU process?
Is it harder to learn the score? You might think so, but I think it's an empirical question. So for us, it didn't seem to matter that much.
I see. Because when you reverse the process, like in standard sampling literature, the underdamped Langevin can separate the position and the momentum term, right? So that's why I think that you can get like a higher order in terms of the discretization error. But when you reverse the process, the drift is now dependent on both the position and the momentum. Right? So I guess in previous work called like sampling is as easy as learning the score. It doesn't seem to find an approach to prove like you can gain a benefit in terms of discretization error when you incorporate the momentum within the diffusion model set.
Yeah. Okay, I don't know about these sort of theoretical arguments that you just brought up. It sounds like a little bit, yeah, but like I can only talk about like empirically it sort of worked out, right? No, those are great questions to ask, and I'm very happy to chat maybe offline about it. But yeah, generally there's no technical problems. It sort of worked out, and yeah, I mean, okay, whether these samplers are really faster than sort of the position space only samplers is a more complicated, a longer answer to that, but maybe we'll get there later. Good. Thanks for your good questions. All right, so can we do something about improving the geometry? So this relates to what we call conjugate integrator. Conjugate integrator, the idea is roughly as follows. We have a problem that we are interested to solve in the original space. Instead of doing that, we apply a deterministic transformation. We go into a different coordinate system. We solve our sampling problem there. The deterministic transformation is called phi. And once we're done with sampling in the new space Z hat, we actually go back, and our original problem is solved. Right? So this is sort of the main idea, and the hope is that while the original problem might be ill-conditioned, maybe it's better behaved in this new space. The important part here is that this trick can be actually applied to any trained model. So you don't actually need to train these models yourselves. You can kind of just download the model, apply these transformations, and then hopefully benefit from the improved results. Okay. So how does this roughly work? Well, first of all, restrict ourselves to linear transformations. So z hat is now a matrix A multiplied with z. A can be time dependent. We also need to know about the connection between the score S and the noise that we inject in diffusion processes. So maybe just this is like a little technical detail for introducing the notation. Please bear with me. And it turns out that if I define A to be the solution to this certain matrix integral that I write here, right? The exponential of B, a time-dependent matrix B, which is an additional force, minus F, the original force, plus G transpose times Z skip, and also define phi in terms of this matrix integral over time. It turns out that plugging those solutions into the original equation simplify them in a way that I can actually eliminate the drift term completely. Right? There's no longer an explicit dependence on F. I can actually remove the entire first term here, because if B equals to 0, this is like an arbitrary free parameter, I get a very simple equation, namely that changes in z hat are just given by a time-dependent coefficients times the noise. This turns out to be equivalent to DDIM if B equals to 0, and it generalizes DDIM, this kind of very popular sampling method, for arbitrary M. It turns out that setting M not equals to 0 actually generalizes DDIM and can enhance its stability. It also applies much more broadly, not only to position space only models, but to the broader class of augmented diffusion models that we just talked about earlier. Skip some theory for the sake of time. Now, it turns out that it's particular for these momentum-based or momentum-augmented diffusion models, we get like almost an order of magnitude gain if we perform this change of coordinates. In orange, you see the quality dropping as a number of the function evaluations of the neural network for the Euler method. And you see that you only get results with very, very large numbers of iterations. Whereas after the coordinate transformation, you actually get a really rapid drop. Right? And in particular, you can also play with this parameter B, which actually is an additional regularization that you can apply that can actually ultimately enhance the stability of your stochastic differential equation. You can even make them faster and drop faster. Everything gets even more exciting if we look at so-called inverse problems. What are inverse problems? Inverse problems are problems where you basically have your original data X, you apply a degradation operator, which is often considered to be linear, and this gives you a degraded signal Y. Right? Sometimes you can also add noise to that degraded signal. And examples for inverse problems are, for example, in-painting, deblurring, and super resolution problems. Right? In all of these cases, you have a linear degradation operator, and potentially you add some additional noise. And all of these problems are also very oftentimes dealt with diffusion models, obviously. In particular, you can also generalize this methodology not only to diffusion models, but to a much broader class of iterative refinement models that also include models that are called flow matching. And here are the equations that you would solve in both equations. In both conditions, in diffusion models, the only change really is that instead of the score that only depends on X, now the score is conditioned on Y. Right? So you kind of take gradients of the posterior distribution of your uncorrupted image given the corrupted signal that you observe. And similarly, for flows, you actually have a vector field that is now also conditioned on Y. I'm going to cut this a little bit short, but you apply a really similar trick where you kind of, again, introduce this nonlinear this linear change of coordinates. You define these operators in the way we just did before, and you get a simplified set of equations that you solve. The core idea, without following all the details, is that you actually treat the directions which are orthogonal to the projection operator differently than the dimensions which are sort of in the null space. That are in the complement of the operator's null space. Empirically, this actually really works fantastically well. So what you see here are different inverse problems. Some of them are in painting. So the left column here is in painting. This here is a deblurring setup. This here is a super resolution setup. We have another deblurring task and another super resolution task. One of them is, again, always done with diffusion. The other one with flows. And PyGDM, the baseline, is actually a highly popular baseline by NVIDIA. It's fairly recent. And by only changing the equations and simulating them differently, we could actually get much better visual results with only 5 neural network evaluations, which is the sort of extremely low budget regime in diffusion models that everyone is interested in accomplishing, right? You want to be able to generate images with very, very few diffusion steps. You can also look at a video. If you take regular integrators and you look at this sort of the blurring setup, the dog gets sort of slowly reconstructed. But basically, in the same steps, I don't know how well you can see this, you get actually qualitatively much better results in relatively few neural network evaluations. You can also look at boring tables and see that basically, with the improved sampler, you get sort of fairly good results in just a handful of steps. Yeah.
How do you think this might apply to nonlinear inverse problems?
Yeah, this is actually all much more complicated, right? Because then also the whole sort of mathematical transformation relied also on linear transformation. So if that becomes nonlinear, then everything gets tricky. I'm not sure if it really applies one-to-one. We did actually some experiments, and practically it seems to work, but there's no theoretical foundation why it should work. Yeah. You can basically pretend that the nonlinear problem is linear, so you can linearize it, and then you can do something similar. And it sort of works empirically, but there's no good theoretical backing.
Just what kind of nonlinear inverse problems were those? Were they like phase retrieval?
I think we looked at sort of JPEG artifact removal, for example. Yeah. Mm-hmm. Yeah. All right. Okay. Quickly look at the time. Yeah, pretty much halfway through. Yeah, so I also promised you that there's going to be a data communication and compression component to the talk. So let's talk briefly about this. And to this end, I have to actually look at diffusion models in a slightly different lens. Turns out diffusion models can be understood in at least 3 different ways. You can look at them as iterative denoising models. You can also look at them as models that learn to reverse a stochastic differential equation, which so far has been basically the perspective taken in this talk. But you can also think of them as deep hierarchical variational autoencoders, in particular if the time is discrete, right? In this hierarchical variational autoencoder perspective, you can actually show that you're optimizing a variational lower bound to the data likelihood, shown here. And this one actually couples into a series of steps, of time steps, where in every such time step, you have a little bit of entropy increase, right, as you go sort of through the chain. Right? If you reverse the process, this term exactly measures how much entropy is reduced in each of these reverse diffusion steps. Now, the question is, if I have a diffusion model and you have a diffusion model, and I generated an image and I generated a sequence of random numbers, can I communication efficiently transmit that series of random numbers to you so that you can exactly reproduce and get the same image that I got, right? In other words, can we use these diffusion models as data compression methods? This problem has a theoretical solution which is called relative entropy coding. Relative entropy coding is a so-called compression without quantization approach, which roughly works as follows. It's very much grounded in Bayesian methodology. Imagine you have a sender and receiver, Alice and Bob. Both of them share a prior, P, here in in red. And Alice would like to transmit a sample from the posterior distribution in blue up to Bob. Right? So we're only interested in this sort of lossy setup where we only want to transmit the sample, right? Now, how do we convert the sample into a series of bits? It turns out there is an elegant solution. Namely, if both of them share a random seed, then Alice can basically sample as many times as it takes, such that she ends up sampling from the prior in such a way that this corresponding sample also has high likelihood under the posterior distribution. Once Alice has found the sample, she transmits the index, how often times she had to sample, maybe 10,000 times. And then Bob reproduces this 10,000 sampling steps and ultimately ends up at exactly the same sample from the posterior. Now, this is called compression without quantization, and it can be applied in theory to diffusion models. The idea then would be exactly as I described before. We would basically transmit successively samples from Alice to Bob. Right? Maybe she starts with a very rough image, then conditioned on that, she generates a number of samples. In each of these samples, the cost to encode them would be fairly small, as long as the prior, P of z, s given z s plus 1, has a high overlap with the posterior distribution that she used. The unfortunate news is that this works only in theory. And in practice, this approach works fairly horribly. In particular, you can imagine if the prior and posterior have very low overlap with each other, it takes a very, very long time to sample until you hit like a high likelihood sample under the under the posterior, right? So this is only like possible in theory. But luckily, there is a practical solution, which is called universal quantization. I don't really have time to talk about it. But it requires a complete redesign of the diffusion process. Essentially, we have to convert Gaussian distributions into uniform distributions. But this sort of messes everything up, and you have to really think about how you set up the whole process. It's a long story that we actively work on. So in the similar sense as Isong, who really set high standards for talking about ongoing research, this is something we currently work on. Now, the exciting part is that it works reasonably well so far, not really as well as we hoped. But here is an example of this progressive compression, right? We have a sample shown here from CIFAR. We start with random noise, and then we transmit more and more bits. And then the receiver can basically successively improve its own estimates of the ground truth image, right? So you see basically that the bits per dimensions increase, and the PSNR, the image distortion, sort of monotonically decreases. All right, let's talk a little bit about the other side, right? I talked about like how can the physics perspective help designing compression models? How can the physics perspective help improving diffusion models? But let's talk a little bit about how diffusion models can actually work well and kind of provide new insights in sort of thermodynamic domains. And one thermodynamic domain is, of course, climate modeling. The dilemma in climate modeling is roughly as follows. You want to essentially simulate the atmosphere at a very, very high spatial resolution, but you also want to simulate it for a very long time, ideally 100 years, right? And ideally, the spatial resolution should only be a few kilometers. This, as you can all imagine, is enormously expensive, right? So usually, we're facing this dilemma that we can either have a really nice spatial resolution, or we can actually simulate the dynamics for like a long time. But there's usually both of this is usually not possible. What you see on the right-hand side is kind of to give you an example of the spatial resolutions that we're interested in, right? So this is the Earth. We typically divide up the Earth into these different tiles, and then climate scientists have their models to simulate precipitation and other physical quantities spatially resolved on these different tiles. The problem is the less we resolve on the small scales, the more and more bias we introduce, right? Because everything at the scale of a few meters will actually feed back into our climate model, right? Clouds, the local fine-grained textures of clouds have a huge effect on how much, for example, radiation is scattered back into space. You really want to simulate the surface of these different clouds. You want to simulate how ice is formed and so on and so forth. All of that really requires very small spatial resolution. The question is then, can we use generative modeling to essentially take a low-resolution climate simulation and super-resolve it so that it sort of almost looks like if it came from a true, expensive, high-resolution climate model, so that we can then ultimately study the climate dynamics over many, many years. Okay? Just as an aside, if you're interested in this domain, there's been a recent dataset release on climate modeling, and I'm primarily showing you this to kind of get a feel for the different spatial fields that are available in this domain, right? We have, for example, there's specific humidities, we have surface pressures, we have temperatures, and so on and so forth, right? So those are typically, you can think of that as a multi-channel image, typically like 30 different channels and spatially resolved and also temporally resolved, right? So it's really sort of a 5-dimensional tensor, I guess. Yeah.
Are people confident that they have a complete representation of climate modeling, or are they missing?
That's a great question. So I would say, since they're ultimately solving the Navier-Stokes equations, fundamentally this should be sort of a complete set of quantities, right? But as soon as you enter the neural network domain and you kind of drop a couple of these, the system is no longer complete. And actually, by leaving out this information, you ultimately make the system stochastic, right? The original problem is deterministic, but by sort of ignoring certain variables, you make it effectively stochastic. So this is the data that we would like to analyze. This actually comes from a collaboration with the Allen Institute that also has a small but very nice and highly competent climate group. And what we would like to do is we'd like to take a course simulation of, in particular, precipitation, in other words, rainfall fields. And we'd like to apply video super resolution to super resolve it to the scales of interest. Okay? So this will allow us to run a cheap model to simulate many years. And again, you can think of the super resolution as a as a post-processing step to get to the quantities of interest. I'm going to cut like a long story short here, but we worked actually a lot on these video super resolution models for as long as they were still computationally tractable. So here's an architecture that worked pretty well for us in practice. So we start with the low resolution reference precipitation field. So you can think of this as a low resolution reference video. We then have a downscaler, which you can think of as a deterministic super resolution module that takes this precipitation field and increases its resolution deterministically by solving essentially a regression task. The problem with super resolution by regression is that you create a lot of mode averaging, right? Because it's a one-to-many mapping, right? When you do super resolution. If you treat it as a regression problem, basically you will learn the average mapping. And the average of images typically looks blurry. And also in this case, the precipitation fields that you then learn are sort of blurry precipitation fields. This is actually particularly bad, and I'll get back to that in a moment. Ultimately, we're interested in sort of crisp, high-resolution precipitation videos. And therefore, we also need a residual. Right? This residual is coming from a diffusion model, which in turn is conditioned on the low-resolution precipitation video. Right? So this is the whole architecture. Well, why didn't we just directly generate the high-resolution video? It turns out that this residual idea works better. This is actually an interesting observation that whenever you do super resolution with diffusions, it's sometimes much better to first sort of make a deterministic prediction and then only generate the stochastic residual, for the reason that sparse images are generally easier to compress. And so also residuals are easier to generate, right? And yeah, so it turns out that generating a sparse residual with diffusion models is better than directly producing the high-resolution video. So here's some results. Those are one of these sort of tiles that I showed earlier. Also turns out when we treat this as a single frame, in other words, frame-by-frame super resolution models, you lose a lot of important temporal context, and the corresponding results don't show like the right amount of details that you would expect, right? The model has to make certain things up. When you kind of treat it as a temporal video resolution problem, you get sort of much better results. And now here's the most important criterion, namely the physics, right? If I use super resolution, and I look now at physical quantities of interest, which is, for example, the annual rain in a particular region, do I introduce biases or not? Right? So here in blue, you see the rainfall distribution in a particular region, or average across all possible regions in blue. So you see density, and here are precipitation quantiles. You want to get as close as possible to this blue ground truth. And whenever you treat super resolution as a regression problem, because of this washing out, this sort of blurriness, the sort of mode averaging that I talked about, the consequence of that in precipitation fields is that you're basically washing out all the high-intensity regions. And as a result, you totally underestimate the extreme events, right? Whereas in diffusion, which is a stochastic approach, you can actually get pretty close to the ground truth precipitation distribution. You can also look at annual averages. So here is the coast of California, right? The topography map. And then this here are annual averages of ground truth and super resolved predictions. Here, for example, is the reference signal, which is very, very coarse. You actually get a pretty nice agreement between both. This is, of course, also in part because the super resolution model is actually allowed to hard code the topography maps, right? So if you think about it, right, if you make a prediction locally in a mountain range, of course, you're allowed to kind of present that mountain range as a reference signal, right? In some sense, you're sort of overfitting to the local geography, but that's fine. You're not interested in new worlds. You're only interested in predicting future times, right? So it's OK to hard code the localities into that model. Yeah, this kind of brings me to the end of my talk. I highly recommend here in the audience, but I guess this is the wrong audience because you're all sort of interdisciplinary already, but we really learned that it makes a lot of sense to look into sort of adjacent literature. For example, books on molecular dynamics give a high degree of inspiration for developing new samplers. Some of the ideas we developed were inspired by these methods. And I would like to thank particularly my PhD students and summarize. I talked about thermodynamics of diffusion, where we talked about the origins of diffusion in thermodynamics. We can adopt many ideas such as physics-inspired generative processes, but we can also learn to generalize between physics and come up with our own unique samplers by drawing in complete recipes. We can design new samplers, and we also learned that diffusion models give rise to efficient progressive coding schemes. I also talked about diffusion models for thermodynamics, where climate data can be a really nice playground for generative modeling, in particular also for video modeling. And it really requires stochasticity because ultimately we care about distribution level quantities. For example, annual precipitations, which you would basically completely get wrong if you treat it as a deterministic setup. There are many interesting open questions that give inspirations for future research. For example, how to incorporate the right physical constraints into your modeling, how to sort of do the proper distribution matching if you have different climate models, one cheap, one expensive, and also kind of theoretical analysis of diffusion models with dynamical phase transitions. I find like a fascinating area for sort of approaching the topic more theoretically. With this, I'd like to close, and thank you so much for your attention.
Which was just on the very recent slide where you're saying, like, in one case, you're kind of getting smoothed out examples. Yeah, this one. Were you saying, like, so the second one is like if you have a multi-frame prediction versus, like, was the middle one doing sampling? Or was it just like whether or not you were?
No, this is kind of a single sample. Yeah, all of those are single samples.
Okay.
The difference between the left and the middle one is this one is sort of doing an image stochastic super resolution, whereas this here is sort of a video super resolution. So this one really takes sort of time continuity into account.
Wouldn't that indicate, like, if you can't predict from a single frame, doesn't that indicate that there's some sort of hysteresis or like hidden variable that you would need in order to get the full fidelity? I guess it's not clear to me, like, why the multi-frame should necessarily be better unless like the single frame just is lacking a certain amount of information. And
it is lacking information, right? Because the multi-frame actually looks at like the entire evolution of the video for like 10 consecutive frames. And so it can really draw on the dynamics in the low reference signal, which so I didn't show here actually. Can I interpret
it just that like a single frame is sort of ambiguous?
Yes.
Okay, so like something like hysteresis or...
Yeah.
Okay,
right.
Cool. Thank you.
Okay. So I thought the idea of using diffusion models for compression was a very cool and interesting one. And I guess it sort of, it was not what I expected because, you know, currently for like the very large scale, like diffusion transformer models, they actually spend a lot of time optimizing a latent space. If you've thought about like the interplay of those two things, like, you know, you talked about actually expanding the dimensionality in which you do the diffusion,
right?
But you could actually massively reduce the dimensionality in which you do the diffusion. I guess it wasn't clear to me whether or not you can use that for compression as well.
that's a really good comment. I mean, I get actually these questions a lot. We do a lot of compression work, and turns out that dimensionality reduction alone is actually not so important. If you look at all these sort of state-of-the-art diffusion for compression papers, they actually almost keep the latent space the same dimension as the original input space. The main idea is that you kind of decorrelate information in the original image. And you want to learn like a simplified entropy model. In other words, you want to learn a really good prior in your latent space so that you can do entropy coding. So most of the compression gains actually come from the entropy coding side. So that's my first comment. So like dimensionality reduction alone doesn't really typically buy you that much. The other comment that you have is, I was very brief on the different types of diffusion for compression works. There's also another work we actually also propose at NeurIPS is where you have like a VAE diffusion hybrid model. And in this model, you have like a latent state from a VAE that you use to kind of condition a diffusion model so that the diffusion model is now stochastically able to to synthesize different images that all preserve the same semantic information. And this actually currently still works better than the stuff that I just talked about. But the progressive compression is just like so elegant that I'm interested in almost from a mathematical point of view. Yeah. There's another question on there.
Yeah. Yes. So for the climate, for the weather forecast, like since you're doing stochastic sampling with a diffusion model, does it allow you to have some sort of uncertainty on the prediction?
Yeah, that's a good point, right? I mean, in principle, you get like the whole statistics, right? I mean, if you believe that the diffusion model is learning the right thing, it really learns the conditional distribution of high-resolution frames given low-resolution reference frame, right? So basically, you can, in principle, synthesize all possible completions of a single reference video or a single reference frame, and so you can do statistics over it for sure. Yeah, and this also gives you like some notion of uncertainty.
Okay, and just one clarification. For the training, you have high-resolution images, right, in the training set?
Yeah, in this work, we had sort of like a coarse-grained video and a high-resolution video. Yeah. Right. There's a question over there.
I'm wondering about your thoughts on the type of problems that diffusion model works well versus like where it wouldn't work well.
Okay. Yeah, where do diffusion models work well and where do they not work well? I mean, clearly there's been some efforts on adopting diffusion models in sort of more the symbolic domain, like language and text. And as far as I know, this doesn't work so well, at least at this point, right? I think autoregressive models are much better currently at these sort of symbolic text. But I think for everything that is more like continuous signals, I think diffusion models are fairly good at. In particular, if they're highly compressible, as in the weather setup, right? Yeah, that would be my take on it.
Very naive question. So for the climate models, what is the frontier for prediction at this point? Like, how far ahead in time can you reliably or accurately predict?
Yeah, that's a great question. So turns out that there are studies that sort of benchmark different predictive models and how many days they can forecast, and then you see always that there's like a skill that sort of degrades over time, and at some point there's like the background prediction, which is like the monthly average at a particular location. And typically, I think after 7 days, you're already fairly close to the monthly average, and after 2 weeks, there's no more signal, basically. So I would say there's a couple of days, handful of days. Yeah, I don't know if that's really expected to change much. Maybe, but yeah, there's this intrinsic chaos, of course, right? That's hard to deal with.
Thanks for the interesting talk. Oh, okay. This might be kind of a weird question, but you found that adding noise in both like momentum space and position space improved the performance of the diffusion model.
Mm-hmm.
Have people tried just like, do you think there could be a further gain to like adding another dimension? Or
yeah,
I mean, it probably would mess up your analytic form, but
I guess in principle, yes, right? I mean, it's very hard to tell if there's really sort of a fundamental reason why this works better, right? I mean, from a machine learning point of view, you could just say those are additional tuning parameters, right? You just make the set of possible models more like the space of the search space bigger, essentially, right? But on the one hand side, this is of course more hyperparameter tuning. You could also say maybe it's not worth it. But then if you think about like a startup or like OpenAI who want to kind of produce a lot of images from the same distribution, I think there it probably makes sense to sort of explore all sorts of possibilities, right?
Yeah, because it seems like just adding more like noise could, I don't know, kind of just make the model a bit more expressive.
Yeah, I think that's the right intuition. I guess you could also make the noise correlated, right? So far we have only placed noise on the diagonal. You could also play with correlated noise. We haven't tried that, but yeah, would be surprised if that also helps.
Could you go to the slides about the conditioning during sampling?
You mean in the first part, right?
Mm-hmm. Yeah.
This one?
Could you the slide that has the narrow canyon versus the nice,
Oh, right.
yeah, circular. Yeah. I just wanted to clarify for this integration. This is something that you execute sort of at runtime.
Yeah. Yeah, exactly. So this is kind of really just downloading like a big diffusion model from
Mhm.
OpenAI, right? Not doing any training at all at home,
Yeah.
and just kind of changing the equations of motion
As you execute
as you execute it, right? And basically this amounts to having some time varying schedules potentially
Mhm.
for learning rates and so on. But those can all be pre-computed, right? There's no overhead in doing so.
Is there any way to sort of do this kind of approach so that way you don't have to do it at runtime? Like, could you go and try to just better condition the weights without additional training?
Condition the weight. I'm not sure if I understand.
Like, when in this process you can try to condition the problem better,
Mhm.
and then you do your sampling in the more conditioned space,
Mhm.
and then you convert back.
Mhm.
Is that something that you have to do at runtime, or could you go and try to condition?
Oh, you mean if you also train the model differently, basically, or?
Yeah, well, the model is trained. Is there any way that you could make these changes like reflected in the weights?
Yeah, I don't have a good answer to that. Yeah, it's an interesting question. Yeah, I haven't thought about it. It's interesting. Thanks.
Oh, one more. Sorry, he's got.
Oh, well, someone right next to him. I was curious just on from experience, like definitely there's a lot of opportunities to create better samplers. What your thoughts are practically about kind of distillation and this other kind of family of getting efficiency?
Yeah, I think that's a good comment. I think there are all sorts of parallel developments at the moment, right? On the one hand side, you can change the fundamental equations of motion that we did here. You can also learn to discretize diffusion models as opposed to following some standard discretization recipes. And then finally, there's also distillation, as you mentioned, right? Where you kind of distill a certain model into another one. The problem with distillation is usually that there's sort of a trade-off between speed and coverage, right? I mean, basically, if you distill a model, you're basically making a stochastic model effectively deterministic, which means that you're doing some form of mode averaging, which means that you ultimately restrict your sampling space into a smaller domain that might look realistic, but you don't have any more guarantee that you really cover the entire conditional distribution. And that might be fine in some applications, but I would say for weather and climate, where you really want to capture all the extreme and unlikely events, I would consider that to be a little dangerous. But yeah, at the moment, there's not a clear winner, I feel. There's lots and lots of ideas around, and you can, of course, combine all of this, but that's not how you write a scientific paper, right? You isolate a problem and you solve this very specific problem. But yeah, I don't know which one will ultimately have the most impact. Time will tell.
Great talk. I wanted to ask you, you showed a lot of results on like super resolution, specifically for climate. Do you think there's a big like difference or challenge that's unique to doing kind of like time series forecasts instead of like, the super resolution task? Is there something fundamentally more difficult about that when it comes to using diffusion models?
Yeah, that's another great question. So turns out there are many different architectures for sort of video diffusion models, right? Or time series forecasting with diffusion models. Some of them sort of automatically generate entire blocks of time segments, right? And others are sort of autoregressive. One thing that I always wanted to do, or was wondering, is that you have basically two notions of time, right? You have like the physical time, but then you also have the diffusion time, or you can also call it a temperature, right? Which you kind of use to generate all these residuals. Now, if you kind of run a diffusion process for every new frame that you generate in an autoregressive fashion, this is like an incredibly slow algorithm. The question is sort of, can you align these two times? Can you sort of diffuse in the time domain so that you're not kind of wasting, that those two time axes are basically aligned. So that might actually potentially also accelerate things. And yeah, I think there is some interesting work on stochastic interpolance that we're currently also exploring, where you're trying to sort of essentially coarse grain the dynamics of a physical system using a data-driven approach, and then you can directly simulate these equations in the time domain as opposed to running orthogonal to it. Don't know if that answers your question.
Interesting.
Thank you. Okay. All right. Thank you.